We would like to find where the function f of z equals u of xy plus I v of xy is analytic, where u and v are the cubic expressions, the third degree expressions that we can see here. Let's first mention the definition of the word analytic. A function is considered analytic at a point z0. So there's z0. If the function is differentiable in an entire disk around z0. So the function has to be differentiable at z0, but not just at z0, in a disk, in some disk around z0. The disk could be very small, but nevertheless, analyticity at a point implies differentiability at infinitely many points, all of the points in the disk. Okay, now this function I mentioned, this is third degree, this is third degree. So what about the function z cubed? Is that what we're looking at here, z cubed? What is z cubed? It is x plus iy cubed, which is x cubed plus 3 x squared times iy plus 3x times iy squared plus iy cubed. And let's look at the real part. X cubed, that's imaginary, that's real, that's minus 3x y squared, that's the real part. And then the imaginary, we have 3x squared y. And then I cubed is negative I, so this is minus y cubed with the I in the front there. So this is z cubed. That's not exactly what we have here. We have almost exactly that, but we have a plus here instead of a minus, and we have a plus here instead of a minus. How much does that change things? The function z cubed has derivative 3z squared at every single point in the complex plane, and so the function z cubed is analytic at every point, because at any point there is a disk around that point where the function is differentiable, and you can make that disk as large as you like. But our function has plus signs here instead of minus signs, and maybe that changes things. So to determine where this function is first differentiable, we will use a theorem that we had in the previous section. It's a partial converse to the Cauchy-Riemann equations. The Cauchy-Riemann equations say that if a function is differentiable, then u sub x equals v sub y, and u sub y equals negative v sub x. In the partial converse, if a function is, to determine if a function is differentiable, we need continuous partial derivatives that satisfy the Cauchy-Riemann equations. So we have to calculate these partial derivatives and see where they satisfy the Cauchy-Riemann equations. I'm sure they will be continuous, since our u and v are just polynomials. U sub x and u sub y, v sub x and v sub y will be continuous, so we'll have that. And we need them to satisfy the Cauchy-Riemann equations as well, which are right here. Okay, so our function here, f of z. So our f of z, I shouldn't have used f here for this function, but our f of z here now has u sub x is equal to, let's erase some of these extra markings here. U sub x is, this is u, and this is iv. So u sub x is 3x squared plus 3y squared. U sub y is 0 plus 6xy. 6xy. Now for v sub x and v sub y. V sub x is 6xy, and v sub y is 3x squared plus 3y squared. Okay, let's check the cosine. These are continuous. Okay, no problem there. They're continuous everywhere, at every point in the plane. Now let's check, does u sub x equal v sub y? U sub x, v sub y, they're identical. So u sub x equals v sub y everywhere, at every point in the complex plane. What about u sub y equals negative v sub x? U sub y and v sub x are equal. So they're supposed to be negatives of each other. So we have 6xy for u sub y. We want that to equal negative 6xy. And this equation does have solutions. This is true if x equals 0 or y equals 0. So we can conclude that our function, f of z, that was given in the problem, is differentiable on both the x-axis, which is y equals 0, and the y-axis, which is x equals 0. So f of z is differentiable on the axes and nowhere else, because this second equation is only satisfied if x is 0 or y is 0. So f of z is differentiable on the axes only, nowhere else. So where is f of z analytic? If we take a point on either axis and we make a disk around it, then our function is not differentiable in that disk, no matter how small we take the disk. As long as the radius of the disk is strictly positive, then that disk will include points that are not on the axes, and so our function is not differentiable on any disk. Even at the origin, you can draw a disk around a point at the origin. It will contain points that are not on the axes, and so the function is not differentiable at every point in that disk. So it's not differentiable on any disk, which means that f is not analytic anywhere. Analyticity is a slightly stronger condition than differentiability. Analytic at a point means differentiable at a disk around that point. So that's a harder condition to meet. And this simple polynomial type function with continuous partial derivatives is differentiable only at infinitely many points, but in no disk. And so it's not analytic anywhere. So f is nowhere analytic.